Hello, madam. My name is Sharvin Unlucky Sivakumar. My metric number is CD240031. Okay, today I'm going to present about the introduction of the static project. In the study of static analyzing bridge trusses demonstrates how forces are distributed in a structure at the equilibrium. A bridge truss composed of triangle components connect at dots is designed to efficiently support load like a vehicle and environment forces engineering. Engineering use principle of equilibrium ensuring the sum of the forces and moment at each joint equal zero to calculate force in a truss member. Free body diagram simplifies the analysis by representing internal forces and support reaction, which are the critical balancing structure. By incorporating moment and support reaction calculation, engineers ensure the truss can withstand applied loads, highlighting static role in creating strong and stable structure.
For problem definition, there are several challenges that we may encounter in this period to solve due to the unique behavior of these trusses. Identifying the forces and reaction in each truss member is the main issue in bridge truss analysis. For an example, for vehicle bridge, especially if the system is tested under variable loads, it can be difficult to correctly estimate the internal forces due to the intricacy of joint designs and the interactions between these connected elements. Second is for pedestrian bridge. A carefully designed construction meant to support pedestrians' safe passage while sustaining the pressures acting against it. To guarantee the bridge's stability, a lot of attention is given to the selection of sturdy and durable materials such as steel, concrete, or composites. The results of a well-conducted static analysis is a pedestrian bridge that does its intended purpose by connecting destination and being strong or safe. And also, it focuses on identifying forces and reactions in each member, which is challenging due to the complex joint designs. Key factors affecting truss behavior includes its shape, such as the length and angles of members, material properties, and external loads like vehicles, wind, and seismic forces. Real-life conditions often deviate from ideal assumptions, as truss joints may have flexibility or friction instead of being perfect pins. Unpredictable loads and positions further complicate the analysis, requiring accurate force calculations to ensure the structure's safety and reliability. There are three objectives for our project or case study. The first one is to analyze the forces acting on each member of the truss bridge under the specific loading conditions which we have applied. The second is to evaluate the equilibrium of forces and moments at various nodes to ensure that the structure remains stable under external loads. The third one is to identify the support reactions and to determine whether the design satisfies static principles like, for example, the fundamental principles of statics for the real world applications that we have, such as in design vehicle bridges and pedestrian bridges.
Literature review on trusses on bridges. Trusses are networks of triangular units providing strength, stability, and load distribution. Advantages is high load bearing capacity, material efficiency, and suitability for larger spans. The key principles are statics, ensures equilibrium by balancing force, the sum of fx equals to 0, and the sum of fy equals to 0, and the sum of m equals to 0. Materials, steel and reinforced concrete of first strength and durability. Load distribution, triangular design minimizes bending moments and optimizes material use. The challenges and innovations. The challenges are fatigue, material degradation, and maintenance. The innovations are advanced materials like high performance steel and composites, computational tools, and modular construction for efficiency and remote applications. The real life applications is it's common in railway and highway bridges, used in conjunction with other systems for long span bridges like suspension or cantilever types.
Hi, my name is MD Parvez Ayub Khan Akash. My metric number is AD240155. Now we can talk about the mathematical modeling of this topic, and we can see at the first slide here that the mathematical modeling in this approach we use the static equilibrium concept to model the truss bridge, which is made to in connected parts, and then the method of the joint is applied the analyzing to each joint individually. By using the static equilibrium equation, we can use the Fx equal to 0 and Fy equal to 0. Then we can determine the internal forces and in the member of the connected to each joint. By solving of the forces of each joint discretely, then we can find the forces to truss member without having to consider the very junction at once. And then simplify at analysis. Then we can now we can see the next slide. This slide we can see the two diagram, and the first one is the truss bridge, we can see there that is the truss bridge, and the second one diagram is the FBD, that's called the free body diagram. We can see the two types of diagram are the similar, as you can see that. After that we can go to the next slide. In this slide we can see the analysis, the two type of analysis, as the first one is the dynamic analysis and the second one is the structural analysis. And now we can talk about the at first we can talk about the dynamic analysis. Then we can see the dynamic analysis is of a part of the truss bridge, studies it responds to moving the vehicles and wind and the earthquake, and it avoid the reasons by the checking the natural frequencies and the equivalent stress from the moving load and access the wind, including vibration and the ensure the stability ensure the stability during the earthquake using ground motion data. It's very important for any bridge. Then we can see the structural analysis. As the structural analysis is also very important for any bridge, and then we can see that using the equilibrium equation, the Fx equal to 0, Fy equal to 0, and m equal to 0. Then we can calculate the support reaction and the analyze the truss. The method of joint revolve the force at the each junction, then to determine intention of the compression. The method of the section that can also be used for the some members, and then the critical forces the near joint F, B, G, F and D are the influenced by the truss humidity and the load distribution. At last, the analysis provide a table summarize the force, the magnitude and the characterize. Then we can see the next slide. We can see the assumption is the very important part. The assumption, we can see the assumption a two-dimensional analysis negation out of the plane effects, and because then ignoring the weight the truss members and which can be affected the straight distribution. And then the simplify joint as the pin connected, not counting for the real joint by rigidity, and the limited the static loads, the excluding the dynamics effect like the wind or earthquake. Then the assumption the small displacement of which may not do under extreme loads. Then we can see the next slide. And this is the last slide of the mathematical modeling, and then that is the limitation. We can see that there are many points in the limitation, and at first we can see that the analysis, the two-dimensional, is ignoring the real world effect, and the second one is the weight of the truss members, so is not considered the which could affect the stress distribution. Then the third one is the pin connected joints are the assumed, but the real joint may have some stiffness. And then the fourth is the dynamic factors like wind, the earthquake and the moving vehicle are the ignored. The only static loads are considered, and it's too much very important. And then the fourth and the fifth one is the assumption of the small displacement may not hold the underserved the loads. And the last one is this limitation states the need for the calculation and the consideration of the addition the factors in the real application. And that is my part, and thank you.
Hello madam, my name is Ashwin and my matrix number is 240275. Today I would like to explain about the calculation we did to obtain forces at each member. Firstly, what we did was we assumed that the overall forces and the moment at each trusses is 0, because we assume that this trusses is in equilibrium state. So from that we calculate the forces there. So sigma fx is equal to 0. So ax is equal to 0 because there's only one x-axis force acting there. And then ey is equal to 0, and then ay plus ey is equal to 70. So I calculated the moment at point A, we assume that clockwise is equal to positive. So EY I get 40, there's an error there, typing error there. Then if EY equals to 40, AY is equals to 30. Then later on I calculated the angle in between the trusses. As you can see, the length for the trusses is same, which is 2, and the height is 2.5, same for everything. So the angle we obtain between trusses will be same for all the trusses. So I did a trigonometric function there. So tangent theta equals to opposite over adjacent. So theta is equals to 51.34. Later on, I just straightaway went to calculate members at point A. At point A, there is 4 forces acting there, as you can see in the free body diagram. FAB, FAG, AY, AX. The AY and AX is there because it's a pin, so it's supposed to have AY and AX there. From that, I just get the answer. FAB equals to 51.23 and FAG I get negative 32. It is in compressed because that's why I get negative. Then I went to point D by using the same method, and as you can see, the free body diagram, it has 3 forces acting at point B. So I did the same calculation method, which is sigma fx equals to 0. So by using that, I get FBC is equals to negative 32 kilonewton and sigma Fy is equals to 0, where I get the answer for FBG. Later on, I went to point G by using the same method. I get the answer for FGC, which is 6.403 kilonewton, and FGF 27 kilonewton. Then at point A, there's 3 force acting, which is EY, EF, and FED. The EY is there because it's a roller, so there's a force always acting perpendicular to the surface. So this is EY. As you can see from just now, we get EY is equal to 40 there. So we just plug in the equation here, then the value here, and then I get negative 32.419 in compressed. That's all for point and member E. So I get for FEF, I get 24 kilonewton, and later I did the same resolving at point D. So as you can see in the free body diagram, there's 3 forces acting in point D: FDC, FDF, and FDE. For FDC, I get negative 24 kilonewton, which is it is in compressed. For FDF, I get 30 kilonewton. Straight away I went to point F, and there's only one force that I didn't get, so I just straight away went to sigma fx to calculate the one force, and the answer I obtained there is FCF, which is in negative 4.802, which is in compressed state. Now I'd like to talk about the result that we obtained from this calculation, which is that's the answer for all the members. As you can see, I've listed down the members here and the answer as well. Forces for all members are FAG negative 32 is in compressed state, FAB 51.23 kilonewton, FBC negative 32 is in compressed state, FBG 40 kilonewton, FGC 6.403 kilonewton, FGF 27 kilonewton, FED negative 38.41 kilonewton in compressed state, FEF 24 kilonewton, FDC negative 24 is in compressed state, FDF 30 kilonewton, and finally FCF negative 4.802 kilonewton. That's all from me, but thank you.
In conclusion, the report examines truss bridge analysis using static equilibrium principle to determine the forces acting on its member, highlighting method like a method of joint and free body diagram. It shows that truss bridge effectively distribute loads and prevent deformation with each member undergoing compression or tension to maintain stability. The report also acknowledged and the limitation of static analysis, such as idling joint and ignoring dynamic factors like wind and seismic activity, emphasizing the need of advanced modeling and material. It discussed the importance of modern material and monitoring system to improve bridge longevity and safety, advocating for a comprehensive approach that considers both static and dynamic factor in future evolution to ensure reliable and efficient trust bridge designs. Thank you.